Okay, let's get started. We're going to cover this in a little bit more detail, but I think this is fascinating that you can use these devices as random number generators or physical unclonable functions and who knows what else. So I think understanding these devices will lead to other mechanisms. Okay, well, I'm going to talk a little bit more about security. Basically, we've talked a lot about DRAM. There's a lot into flash memory. And there are a bunch of emerging memory technologies that some of you are working on over here. And I think these all have their reliability problems, which could pose themselves as security vulnerabilities, especially these ones, because these ones are going to be very close to DRAM very soon. Or maybe they'll replace part of DRAM very soon. Right?
What threat model do you have in mind for the security?
Oh, I think, I mean, Rowhammer is one example, right? It was kind of a threat model that is unexpected. Basically, reliability, if you get bit flips, somebody can exploit them. Let me put it that way. I'm using security in a loose manner over here, not a very formal way, yes. Okay, so I think I will advocate principled designs to design fundamentally secure computing architectures. Now, what does that mean? I think it'd be good if we could somehow predict and prevent such issues. And as you can see, I'm using the word safety over here. I like replacing these things because I think with reliability issues, you have both your safety and security is threatened in addition to your reliability. So this is, recall this bridge that I showed you earlier. You may think that we're actually building bridges for a really long time, right? But these things keep happening. Like you may recall this one. This was in Seoul in 1994. People were not as fortunate as the previous one. I think tens of people actually died. This is on the Han River. Yeah. You may recall this one. This is, I think, somewhere in Italy, right? No, that's at Minneapolis. This is the bridge over there. And this is a more recent. This is in Genoa, right? Very recently. So we've been building bridges for I don't know how many thousands of years, and we still run into such problems. Now, you could guess why we have it, why we don't have it. I don't know. But I think in computers, we have the flexibility of modeling better. I don't know yet. So this is my one-slide recipe for potentially architecting for security. Again, very general security with a focus on memory. I think we don't even understand. We should start with understanding. Basically, we need to have methods for modeling vulnerabilities, reliability problems, and maybe somehow discovering them. Like VRT is something that we understood a little bit, but we don't even know how to discover it, right? So I think this has to be done with real device data and analysis. You should, of course, do circuit modeling, device modeling, but something like Rowhammer, I don't even know how to model it at the circuit level or device level. It doesn't, that model doesn't exist, basically. You have to really resort to real device data and analysis somehow. Yeah, basically, somehow we need to understand the vulnerabilities and develop reliable metrics. These are very high level, so I'm not going to go into the details a lot, but I think once we understand it, maybe we can have principled architectures with security as key concern. And maybe we don't even need to understand it to be able to do this. So we need to have good partitioning of duties across the stack, memory controller and memory. I think the duties are really not partitioned well between those two at this point. Maybe operating system and memory. I don't think the duties are partitioned very well across those at this point because not enough information flows between them, right? The memory controller doesn't know enough about the memory that's controlling, and the memory doesn't want to give, and the other way around also. Of course, while we are doing this, we cannot give up performance and efficiency. I think patchability in the field is very, very important, as we discovered with Rowhammer. If you have a memory controller that's patchable in the field, you can do a lot more. I think Flash has this beautiful characteristics right now. Its controllers are patchable in the field, right? You have controllers that are essentially processors. Well, some of them are hardwired, but it's relatively patchable compared to DRAM. Yes? Yes, that's true. In different ways, potentially. Of course, yeah, there are potentially other security vulnerabilities that you can open up with this. But I think, yeah, I understand you. So you need to be careful when you're doing this patchability. And I think on top of this, we need to have designs for security. We know how to design for performance. We know maybe how to design for efficiency, energy. But we don't know how to design for security currently, as far as I understand. And I think online testing is really important. but we need to develop methods for design and automation also. And these testing mechanisms need to be high coverage, and they need to have good interaction with other system reliability methods. We can talk more about this, but this is where I'm going to stop in this slide at least. So that's one of the reasons why we've been developing these infrastructures. I think that's one of the reasons why we've open sourced our infrastructure, actually the SoftMC infrastructure, so that people can use. Because we can only do so much. We can understand model, and we've actually published a lot of models and our understandings. But I think there's a lot more to do in order to understand these devices, especially the newer ones. And that's what we've been doing with the flash memory also. If we have time, I'll talk about flash memory a little bit. Actually, maybe we have time. Okay, this is the paper that I recommended. I'm going to cover a bunch of things. So there are a bunch of vulnerabilities in flash memory also that I'm not going to talk about. It's very fascinating, but we don't have time. But I'll point you to this paper in HPCA. Flash memory is harder to exploit, of course, right? Flash memory is not directly exposed to the programming language. DRAM is directly exposed to your programming language. If you have a bit flip, you'll see it in your program. If you have a bit flip in flash memory, for that to propagate into your system, you really need to overcome layers and layers of things, right? Flash translation layer, first of all, gets rid of a lot of your bit flips inside there. And even if you have bit flips after that, how do you actually take advantage of those bit flips? So this paper puts some sketches into exploiting those bit flips, but this is not a real attack. And I'm not sure if a real attack can be done by exploiting some of the bit flips that we see in real devices. So these are bit flips that we generate in real devices, but it's not clear if you can actually exploit them in real life. Okay, so we've been looking a lot into 3D flash memory also, and I recommend some of the papers over here. And this is the latest one in Sigmetrics. It's about a 50-page paper. Once Sigmetrics switched to the journal format, it's very nice, I think. You can actually write as long as you need to write in a paper, as opposed to whatever is dictated by the page limit of a conference. So I really like the Sigmetrics model in terms of conferences. They basically decoupled the conference from the publication. And the conference, you go and present, you publish a one-page abstract, actually up to 3 pages right now. And the publication appears in a journal, and you keep addressing the comments, and then you publish when it's really ready. Okay, and there's more work that I may describe, but I'm going to give you the choice before we conclude this particular part. So okay, I've talked about some solution directions, but there are 2 other solution directions, maybe to security also. One is new technologies. I'm not advocating this as the solution direction because all of the technologies have different problems as well. But if you can replace DRAM with a better technology, that would be nice. I'm not sure if this is going to happen. All of the technologies have their downsides. I think this is definitely a good solution regardless of the technology. We've discussed this before. I'm going to talk about this very little more. Basically, if we can design memories with different reliability and store data intelligently across them, we can actually enable a much bigger trade-off space than we have right now. I'm going to talk a little bit more. But I think fundamental solutions to security at this point require co-design across the hierarchy. New technologies, for example, you cannot enable it without actually co-designing across the hierarchy. That's true for this one also. So let's focus on this one because we're going to have a full lecture on the new technologies. Okay, I showed you this before. I'm going to go through this very quickly again. Basically, if you can identify the vulnerability of your data to errors, you can categorize your data as vulnerable and tolerant. Or you can have shades of gray of this somehow. And somebody needs to do that. Programmer is probably the right person to do that. So you need to have mechanisms in the programming model to be able to do that. Unless you somehow discover semantic vulnerability automatically, which is, I think, a very difficult thing. And if you actually do that, you can map the data to different types of memories. Of course, this is not an easy, and I already said that we've done it manually for some interesting workloads. Web search was the one that's more amenable to this. We actually looked at graph processing in the same paper, and we found out that graph processing is not very amenable to this, at least at the coarse grain. If you go into the data structure level, maybe you can actually, graph processing is actually amenable to this also, but we don't know at this point. But this is actually a across the stack problem. If you have applications on the top with different data, and you want to characterize and classify their memory error tolerance, and basically have some vulnerability scale, if you will, for some data. And here we have shades of gray, as you can see. And then you map the application data to this heterogeneous reliability memory system enabled by different kind of solutions. And the paper actually covers many, many solutions. Like there could be software recovery mechanisms with parity memory. There could be extremely reliable memory, and there could be completely unreliable memory, right? What do you map where? This is an open question. And I think there's a lot more potential in this direction. I'll give you an example of the results that you can do. This is not a comprehensive design space exploration. And I don't even know how to explore this design space, actually, because we basically came up with some memory configurations. Some of them are, for example, this is a less tested memory, the yellow one. This is heterogeneous reliability memory. And this is heterogeneous reliability memory employing less tested memory. This is a typical server today with ECC, consumer PC that has no ECC. And these are the dimensions that we evaluated our workloads with. Like some example, crashes per server per month, single server availability, incorrect queries, over 1 million queries. And these are the savings that you get if you actually employ these different memories compared to a typical server today, I believe. Hardware cost savings and memory cost savings over here. So ideally, you would like to be outer. Actually, inner is worse. So you can see that less tested memory is not good in terms of availability. In terms of crashes, it's terrible. In terms of incorrect response, it's also terrible. But it gives you a lot of cost savings. It's the highest cost savings that you get over here. You don't want this one. But if you have heterogeneity, you get better trade-offs. This heterogeneous reliability memory covers a good chunk of it. It's not the best over here, as you can see. You give up some availability, and you sometimes get incorrect queries, but you may not care, again, depending on the application. But it's very close to, it's better than others compared to, in many dimensions, as you can see, right? It gets you high savings. If you can tolerate these points over here, it may be a good idea. Okay, this is one example result from this paper. And I think there's a huge design space over here and research that can be done at the highest levels of the programming language as well as the lowest level of the devices. Okay, let me conclude this Rovehammer or memory reliability part. So hopefully I've convinced you that memory reliability is reducing. I don't need to convince you. You may actually be seeing these in your devices. Reliability issues open up security vulnerabilities, and these are very hard to defend against. These are basically Byzantine failures. Well, depending on what kind of failure it is, but Rovehammer is an example of a Byzantine failure. Its implications on system security research are tremendous and exciting. Good news is we have a lot more to do. The bad news is it's not easy. Basically, we need to develop, I believe we need to develop more stronger methodologies for principled designs that can basically identify these failures and tolerate these failures, because we don't want to open up systems to these Byzantine attacks. Okay, so this is the challenge and opportunity for the future, and hopefully this is still the takeaway. So that's the end of lecture 2A. So now there's a choice. We go to lecture 2B, talk about flash memory reliability, less so security, or we go to lecture 3. Who prefers what? Who wants to talk about flash memory? Okay, you don't have a fully informed choice right now.
What's the third one?
And lecture 3 we're going to get to anyway, but that's about in-memory computation.
Oh, like we read that anyway, yeah.
We're going to get there anyway. So this we can maybe cover in the last 30 minutes, and then we can start in-memory computation. Or if you say I don't really care about flash memory, who uses that anyway? Okay, let's take a vote. Who wants lecture 2A? Flash memory. Yeah, 2B, sorry, not lecture. Who wants 2B? Okay, who wants to skip 2B and go to in-memory computation directly? Okay, I think the first set of voters win. So let's do this. I think it's going to be fun. And I can talk about this, I think, hours and hours, but I'm going to limit it to really 30 minutes. And I'm going to refer you to that paper that I've shown many times by now that you're probably sick of seeing it on the screen. So I'm not going to talk about security, as I said. I'm going to give you some basics of flash memory, but not a lot of detail, hopefully. But basically, flash memory is another charge-based memory. And in my opinion, this is actually perhaps the electronic technology that's revolutionized our lives in the last 20, 30 years. If this flash memory wasn't there, I don't think we would have things like this. Now we actually take it for granted, right? This thing is full with pictures, for example. What a waste. Even though it has, I don't know, 64 gigabytes or maybe 128 gigabytes. I even forget. Right? So basically, we take this for granted. But this is really revolutionized our lives. This thing is booting up fast because of flash memory. Okay, let's go back over here. Oh, okay, I don't know what happened. Okay, basically, flash memory suffers from the same problems as DRAM. Reliable sensing becomes difficult as charge storage unit size reduces, and it's actually a much less reliable technology than DRAM. As a result, you need to have a lot of error-correcting codes. So this is a relatively old graph, but basically, and this doesn't even have 3D technology over here. I'm going to give you the scaling trend, and maybe we'll talk about 3D technology, but I don't really have slides for 3D, even though we have several papers on the topic. So basically, this is the effective cell size of flash, and this is how it has evolved over the years. This is 1998, as you can see, and this was about 2012 or so. This is single-level cell. We're going to talk about single-level, multi-level. Basically, you can chop the charge voltage range in flash into multiple levels. Either you can say, I have one reference, and anything below this is 1, anything above this is 0, or vice versa. Or you can say, I have 3 different partitions, and I have 4 levels as a result. I have 0, 0, 0, 1, 1, 0, 1, 1, for example. That's one encoding, of course. You may not want to encode things that way. But this has scaled really well over time. And you can see the cell size has reduced a lot from 0.7 micrometers to 2x nanometer at the time we constructed this thing. And it's still scaling. But at the time while we started this research, it wasn't clear if it was going to scale because people didn't move to 3D technologies. So I'm going to give you the error mechanisms that we observed in flash. And this is one other example. Flash memory has an endurance problem. Basically, you have what's called program erase cycles. You need to erase a block, and then you need to program a page after that. And you can only tolerate so many of these program erase cycles. And this is single-level cell, stores 1 bit per cell. This is multi-level cell, stores 2 bits per cell. This is triple-level cell, stores 3 bits per cell. And as you can see, this is the lithography, and this is the year. And this is the endurance. How many program erase cycles a cell can tolerate? This is about 3,000. This is about, I don't know, 500 or so. And with a single-level cell, you can actually tolerate a lot more. But clearly, you gain a lot more capacity over here. But there's a clear trade-off between capacity and reliability. This is the provided program erase cycles for multi-level cell, flash cell. It's a few thousand. But the required ones, if you look at the storage industry requirements, it's defined this way, basically. You write the full capacity of the drive 10 times per day for 5 years. This is pretty aggressive. And if you translate it to how many program erase cycles you want to do, it turns out it's 50,000 or so. So there's a mismatch between what the technology provides and what the storage industry demands. So how do you get from a few thousand to 50K? That's one of the reasons for the research. And flash controllers do a lot to be able to bridge this gap, basically. One is, of course, use this single-level cell. That's certainly possible. But then your capacity is reduced. OK. So I'm going to treat flash memory as a channel. Basically, you write some data into the channel, and you read the channel later on at some point. And there's a lot of noise in the channel. And what is that noise? Basically, there's a lot of noise in the channel. You want to get the reads correct, basically, at least as correct as what you've written. You want to get the writes correct in the first place also, but we may talk about that. OK, so basically, you have these noisy flash chips. You get some row bit error rate from the flash chips, and this is high. As a result, the controllers need to employ error correction and many different mechanisms, such that the uncorrectable bit error rate is below some standard. Again, human-specified, industry-specified standard. And to get to that row bit error rate, you may need to do some signal processing also. So we're going to talk about some of these mechanisms with a focus on read disturb. So ideally, you would like to lower this as much as possible, and you would like to better your error correction. So our goals when we started this research was to build, so first of all, build reliable error models for NAND flash memory and design efficient reliability mechanisms based on the models. And when we first started looking at this, actually, there was not a lot of data in the field. So we decided to collaborate with industry and put some of these data into the field. And I think when we first started doing the research, we were behind the industry because industry knew a lot. But I think we're a bit ahead of the industry right now in terms of what we know. Not in everything, not in everything. Because we still cannot get access to some of the things inside the real device. So basically, what we wanted to do was to experimentally characterize and model the dominant errors, just like we did for DRAM. And this was the first paper that we've written. I'm going to talk about that. But this is the lifetime of what happens to a flash cell, if you will. In order to write to a cell, you need to erase the block, entire block, and you need to program the page. And you get errors while you're doing that. Erase errors, programming errors. So your write may not be correct. And while the cell is written, it's living, some other cells disturb it. This is called neighbor page. When the neighbor page is programmed or read, you get cell-to-cell interference. Very similar to read disturb errors that we've seen in DRAM. I'm going to talk about that actually. So you get disturbed by other cells. So being a flash cell is not easy. And even if nobody's disturbing you, you have retention issues. Basically, you cannot retain data really well. As a result, you may get errors. And in the end, you want to read that cell. You may not get the correct value because it was subjected to all of these failure mechanisms during its lifetime after it was written. Page and block, I'm going to get to that, yes. Actually, block is much larger. Page is much smaller, yes. And you erase at the block granularity because it's much cheaper to do so in Flash. You could erase at the page granularity at very high cost. So no one uses that. OK. Yeah, and there are more papers that I'm going to talk about. So our goals were to understand the error mechanisms first, just like I prescribed earlier, and develop reliable predictive models for multi-level cell NAND flash memory errors, and develop efficient error management techniques to mitigate errors and improve flash reliability and endurance. So our approach was to have solid experimental analyses of errors in real MLC NAND flash memory to drive the understanding and to drive our models. And hopefully, the understanding models and some creativity leads to new techniques. And that's exactly why we built this infrastructure. At the time, this is about 2011 or so. This is very similar to our DRAM infrastructure. It's a NAND controller with access to some special commands from the flash manufacturers, such that we can actually, in a more fine grain, read the voltages of different cells. I think infrastructure is really important. This took about 1.5 years to build also and calibrate. So what are the error types that we get? This is based on our first paper. There are 4 types of errors. 3 of them are caused by common flash operations. You get read errors, you get erase errors, and you get program interference errors. Basically, whenever you program a cell, something else around it gets disturbed. And you also have errors caused by flash cell losing charge over time. Even though flash is non-volatile memory, there are still retention errors. So it's really not non-volatile. And we're going to introduce refresh into flash. So whether an error happens depends on the required retention time, of course. How long you want the data to be there inside the device. If you want it 3 years, it's likely that you're going to get retention errors, especially if you're worn out the device. If you want it there for 1 day, maybe you're OK. Depends on the age of the device, sorry. And this is especially problematic in MLC, multi-level cell flash, because threshold voltage window to determine the stored value is smaller. Basically, you chop the threshold voltage window into, OK. If I write over there, will you be able to see? You will be, but maybe the camera will not. So I don't see Roman, so I'm going to be conservative and write over here. Actually, I may have that in the next slide. No, I don't have it. So basically, if you look at flash memory, this is threshold voltage of a cell. Basically, threshold voltage determines what's the value stored, and this is the probability distribution function. And in a single level cell, what you have is you have a read reference voltage, and everything below here is a 0, everything above here is a 1. And what you usually get is a distribution because of the properties of the cell. Basically, some cells are close to here, some cells are farther away from here. And this is called the threshold voltage distribution of the flash. Now, this is nice because you have the full threshold voltage range divided into 2. But if you want to store more bits per cell, what happens is you divide this into 1, 2, yes. No, that doesn't work, right? 1, 2, 3, 4. Yeah, that's better. Now you get 0, 0 here, 0, 1, 1, 0, 1, 1, let's say. Well, OK. I made a mess here, right? OK, I'll be able to do it better. Let's see, 1, 1, 1, 0 over here. And this is a distribution. Now these distributions are much closer to each other, as you can see, because the voltage range is much smaller. And if you want to store 3 bits, there are 8 of them, and those are even smaller. That's why you get more errors with MLC, multi-level cell, and triple-level cell. OK, so when we did our first study, this is from the original date paper. Yes?
Gray code is by design or just, randomly?
I put gray codes over here by design, yes. So that, yeah, exactly. But there's a more theory in terms of what kind of codes you want over there. But that's a good catch. Okay, so this is real data from the devices that we've tested. They're relatively old devices, 2011 or so. And this is what you get in the devices. So this is the program erase cycles the device is subjected to. We call that how many times you programmed and erase things. And this is the raw bit error rate. As you can see, the first conclusion is that raw bit error rate increases exponentially with program erase cycles. This is logarithmic, as you can see over here. So as you wear out the device, as you keep writing and writing and writing and writing, your error rate increases exponentially. And there are different types of errors. If you look at the errors, retention errors are the dominant ones. So these top parts are all retention errors. And some of them are assumed 3-year retention time, 1-year retention time, 3-month retention time, 3-week retention time. 3 days here, 1 day is actually here. What does this mean? Basically, you want to keep the data 3 years. You write the data and read it after 3 years. What happens in between? You get errors, especially if you've already worn out the page. So you can see that the dominant ones are over here. More than 99% of the errors for 1-year retention time are your retention errors. There are other errors, program interference errors, as you can see over here, read errors and erase errors that we may talk about later on. But that's the key observation. Retention errors are dominant, and retention errors increase with retention time requirements, because it's more likely that the flash cell will fail before you read it if you read it after a long time. Okay, that's very interesting. The methodology also is very interesting, but I'm not going to talk about that over here. And this is the paper. If you're really interested in real data from real devices, this was very hard to come across until 2011, 2012, at least in public literature. Yes? No. So what this means is, if you look at all of the errors that you observe over here, more than assuming a 1-year retention time, assuming that you read all of the cells after 1 year, 99% of the errors that you observe are retention time errors. Everything else is basically not important. Yeah, after 1 year it's retained. If it's 1 day, it's not 99%, as you can see, right? It's this yellow thing over here. It's still high, but it's not as high as the program interference errors, although they're relatively close, right? Yeah, the 1 day is the yellow one. That's the 1 day retention error rate. And the green one is the program interference errors. Yeah. Okay, but 1 day is, usually people read much longer than 1 day, right? Flash devices. Okay, so that was the beginning. So solution to retention errors. What is the solution? Basically refresh periodically. And change the period based on the program and erase cycle wear out. So how do you do the refresh is very interesting, is Flash. So you refresh more often at higher program and erase cycles. You start with no refresh. After some time, you go into refreshing every week. After some time, you go into refreshing every 3 days. After some time, you go into refreshing every day. After some time, you go into refreshing every hour, let's say. And you're close to the end of the lifetime as you keep refreshing. And actually, Flash is interesting because whenever you need to refresh, you may need to rewrite the data somewhere else, but we also propose in-place refresh because when you're refreshing, you're strictly injecting charge. Refresh, so retention loss means that this distribution over here shifts to the left. So this is the shifted distribution. As a result, you get errors because you read with the same reference voltage over here. So if you want to refresh, you want to inject more charge through incremental step pulse programming in Flash, you basically shift the distribution back to the right. So that's called in-place refresh. So if you do in-place refresh, actually, you're programming the cell, but now you're introducing programming errors. So there's a trade-off. To get rid of retention errors, you want to do in-place refresh. But when you do in-place refresh, you're programming the cell and you're introducing programming errors. So our solution was actually to use a combination of in-place refresh and remapping-based refresh. Remapping-based refresh means if you actually want to refresh the cell, write it somewhere else. That way you don't introduce programming errors in the same place over and over. And the paper has a lot more detail. And this shows that you could actually improve the lifetime significantly, like more than 47x or so, if you actually do this right. And as far as I know, all of the commercial SSD controllers that are employed in data centers are using this sort of refresh today. They need to, because they need to guarantee that endurance requirement. And if you're interested, this is the work. Question? Okay, no question. Okay, so there are a bunch of other areas that I'm not going to cover. This is really interesting, actually. This is from the recent paper, the like 40-page paper that I mentioned earlier. For example, these are different error types: program error cycling, program interference, cell-to-cell interference, data retention, and read disturb. And there are a bunch of different mechanisms that are proposed in literature. Not all of them cover all of the errors, and ECC is not even talked about over here. But ECC is a very inefficient method for covering refresh, retention errors, for example. Retention errors can be covered much better with refresh. So if you're interested, you can go into this. But I'm going to focus on read disturb errors because we talked a lot about rowhammer. Actually, read disturb is very common in any kind of memory. All scaled memories are prone to read disturb errors. DRAM, SRAM has read disturbance. Hard disks have something called adjacent track interference. When you actually read or write to a track, you actually disturb the adjacent track. And NAND flash has it. So let's talk about the NAND flash as an example. This is the pictorial view, high-level view of a NAND flash memory. You have these blocks, and each block has some number of pages, in this case 256. And as I said, you erase the entire block. But you can read a page. So in order to be able to read a page, what happens is you need to actually access the entire block. Because this, to make it really dense, all of these things are connected as a string over here. And the sense amplifiers are at the bottom. And what happens is you need to apply a read reference voltage over here. And you need to ensure that these other things that are connected to the bit lines don't interfere with what you're reading. So you need to apply a higher voltage called pass-through voltage to all of the other pages in the same block. Now that introduces read disturbance. Basically, let's go back and let's pick this part of the block. So this is your block, this is your page. Sense amplifier is very similar to the DRAM, right? Except the technology is very different internally. So this is what flash looks like. This is the bit string over here. And we're going to focus on this bit string. So this is the row. And that's how you activate the word line, and that's the column. You know about that. So if you look at a flash cell, it has the floating gate and the drain and the source. And it has a threshold voltage that basically enables it or disables it as a switch, if you think about it. So if the read reference voltage, if the read voltage is greater than the threshold voltage, basically the flash cell passes whatever value. It acts as a connected switch. So you get whatever is passing over there. If the read voltage is smaller than the threshold voltage of the cell, then you inhibit whatever is passing. So the switch is off, basically, in that case. And threshold voltage, how do you determine the threshold voltage? By programming. Basically, if a cell is programmed to 0, 0, its threshold voltage is smaller. If a cell is programmed to 1, 0, its threshold voltage is higher. So threshold voltage is programmable. And that's exactly how you store the data. So data is stored in terms of threshold voltage. And if you want to access the data, you want to apply a read voltage, yeah, like this, basically. That's okay, let's do the reading. So if you want to actually not read what's in the flash cell, you apply a pass-through voltage. Basically, you want to pass whatever comes from the top. You apply a very high voltage, high enough voltage, that's greater than everything else over here. And that ensures that the things that are not read pass the data down. That's the idea. So let's take a look at an example. This is our small flash array. This is our flash array that's programmed to these values for whatever reason, and we have 4 pages. And let's say we want to read from page 2. We apply the read voltage, 2.5 volts over here, and we apply the pass-through voltage to everything else. And if we do that, what happens is, because these are large enough, all of these pages that are applied the pass-through voltage pass whatever comes through them. But these two things are inhibited because they have threshold voltages that are greater than the read voltage. As a result of this, you get 1s over here and 0s over here, and you correctly read this page. That's the idea. That's the reading mechanism. Now, the problem is this reading mechanism causes read disturb. It's a very different read disturb than DRAM because you cause a weak, well, in nature it's similar, but the way it manifests itself is different. So it has a weak programming effect. So let's say we're repeatedly reading page 3, or any other page than page 2. Okay, I'm going to try to animate this. It's a bit ugly animation. Okay, so we repeatedly read page 3 many times, which means that we repeatedly applied pass-through voltage to page 1, page 2, and page 4. Because of this weak programming effect, very high pass-through voltage, we had 5 volts over here. This flipped from 2.6 volts. Oh, okay, sorry, I didn't do that well. Yeah, that flipped from 2.4 volts to 2.6 volts because you applied very high voltage to it. Now that's a problem. Now let's go back and read page 2. If you read page 2 now, you get an error because your read reference voltage is 2.5 volts, and this is at 2.6 volts. You get a 0, but it should have been a 1. It just flipped because you read some other page in the same block, or many pages in the same block many times. As a result, you applied the high pass-through voltage to this, and you flipped a bit.
So except for this transient error, does this also...
So this not, this is not transient.
It's not transient.
Yeah.
You're right.
Mm-hmm.
It stays.
Mm-hmm.
I'm sorry. But it also affects, does it also affect the endurance in long run?
Yes, it does. It does actually.
So
Yeah, it affects a bit the error rate. It affects the endurance.
So this weak programming basically eats away the endurance.
Exactly. That's one. Yeah, exactly. Okay. So if your ECC can correct this, that's great. But this eats away from your error correction capability of your ECC. So basically, this is what we analyzed in our DSM paper. They actually limit flash memory lifetime today because if you get rid of retention errors, if you get rid of some of the other errors that I haven't described, read disturb errors remain, and you need to handle them. Because of this, there's a problem. I said this already. So basically, we characterize this read disturb phenomenon on real flash chips, and we basically propose several mechanisms. If you actually slightly lower VPass, you greatly reduce read disturb errors. You don't need to apply the highest over here. You can actually apply it on a per page basis because the real cause of the problem is this high pass-through voltage. Okay, that's one idea. And the second idea is some flash cells are actually more prone to read disturb, and you can actually do probabilistic analysis of flash cells to recover the data. We call this read disturb recovery. I'm going to give you the basic idea very soon. Okay, this is the first technique. You mitigate the read disturb errors online. It's called VPass tuning. You dynamically find and apply a lower VPass per block. There's some overhead, but the lifetime improves significantly. And the second is you recover after failure. Assuming that your ECC, everything failed, your drive failed, you can still recover after a failure to prevent data loss. We call this read disturb oriented error recovery. You selectively correct cells more susceptible to read disturb errors. I like these probabilistic mechanisms, so I'm going to talk about the second technique a little bit. This reduced the robit error rate by up to 36% according to our results. So what's the idea? So this is the same distribution that I drew over here. This normalized VTH, the probability distribution function. There are some cells that are resistant to read disturb. There are some cells that are prone to read disturb. If it's resistant, it doesn't move in the... Whenever you get disturbed, your threshold voltage increases, actually. If you're resistant, you basically stay almost at the same place. If you're prone, then you move a lot in this threshold voltage distribution space. So let's assume that these are the two states, erase state and P1 state. And let's assume that these are the circles are in erase state and squares are in P1 state. Now let's say we apply 250K read disturbs. What happens is distributions shift, but the resistant ones stay in their distribution. Prone ones actually cause issues. They get mixed with the other distribution. So it turns out disturb-prone cells have higher threshold voltages in general, as you can see over here. Disturb-resistant cells have lower threshold voltages. So the problem that we have is basically we need to identify what is where. And that's what we would like to do. This is the idea. So whenever you have an uncorrectable flash error, normally your device fails at that point in time. You back up all the valid data in the faulty block because you know where things are uncorrectable. The idea is to explicitly disturb the faulty page 100 times, 100,000 times or more. Now this causes read disturbance. You know the initial threshold voltages. You know the threshold voltages after that huge read disturbance that you explicitly caused. And you can compare the threshold voltages before and after read disturb. And you select cells that are susceptible to flash errors, basically things that are close to the threshold voltage, that are close to the reference voltage, whose threshold voltages are close to the reference voltage at which you read. And you predict. among these susceptible cells, if you see cells that have very high threshold voltage shifts, you say, oh, they're disturb prone. So they must belong to the higher threshold voltage state. And if you see cells with less threshold voltage shifts, then you basically guess that they're disturb resistant. So you predict that they belong to the lower threshold voltage state. And then you go back and say okay, these are the real values that I expect from this, and apply error correction again. And if your error correction passes, then that's good. So that's the idea. I described this very quickly, but it all boils down to the fact that, yes.
The formula there, you have the same thing on both sides. It's supposed to be plastic. There should be plus sigma there. No.
Which one? This one? Yeah, there should be a plus. I'm sorry. Yeah, this should be plus. That's a very good catch. Yeah, that should be a plus. Basically, if a cell is read disturb prone versus read disturb resistance, that determines which distribution that you predict the cell was originally in. That's the idea. And it turns out you can actually reduce the total error count significantly. And you can use the ECC to correct the remaining errors. And that's the paper if you're interested. There's a lot more to describe in this. I'm not going to have time to do that. I have still 2.5 minutes. But I'm going to point you to some papers. We've actually been doing large-scale studies as well in Flash. And this is really interesting to see in real effect. But of course, we don't have enough visibility and control over the real systems.
So when do you do this process?
Oh, when do you do that?
Yeah, I mean, you cannot really put the information on every cell, whether it's...
That's right. You do it only
when you need to recover.
Exactly. Exactly. Basically, normally what happens is if you get an uncorrectable error, your drive fails.
Okay.
At that point, you either say, oh, my drive failed. But if you want to recover the data from your drive, that's when you do the process. And if you recover the data, you can keep going, right, potentially. Or you could back it up to some other place. But at least you'll recover the data. Yes?
Can you manipulate the read voltage too?
Yes, you can manipulate the read voltage too, sure. And there are actually other mechanisms. Some of these proposed mechanisms to manipulate the read voltage to minimize the error rates. And actually, a lot of flash controllers do that today. They manipulate the read voltage. Whenever the distribution shifts, for example, they also shift the read voltages so that they can they can minimize the error rates. And actually, the manipulation of the fine-grained manipulation of the read voltage is what enabled a lot of our studies. Today, if you want to manipulate the read voltage on a flash chip, you have an interface, but that's a very coarse grain. You need to really know what those special commands are to be able to get to the voltage distributions. Yes? The read disturb recovery technique that I just described? As far as I know, no, it's not implemented. But this is, as far as I know, it makes sense also.
There's a lot of IPs to manage that, otherwise nothing would work.
Yeah, exactly. So there are some things that are implemented. If you want to really know what's implemented and what's not, I would recommend looking at this. Basically, this talks about things that have been implemented and things that are more researchy. We cover a lot of literature over here. Okay. This is not moving. So I think there are a bunch of other works that I'm just going to recommend. We don't have time to cover them. But certainly there is a lot here. I think it's a fascinating area. We've studied threshold voltage distributions, which is really interesting. And you can predict actually threshold voltage, how they're going to shift. You can model them. As a result, you can shift the read reference voltage, as you mentioned, based on your predictions. This is, I'm going to skip that. But this is actually interesting. Here, because whenever you program a neighbor cell, you disturb the adjacent cells. Whenever you get an error in the adjacent cells, you can guess what the value you have is, if you have an error, based on the values of the neighbor cells. That's the idea over here. Because your neighbor cells, when they were programmed, they affected you. And if you get an error in yourself, you go back to your neighbor cells and use them to build confidence in terms of your own value. This is called neighbor-assisted error correction. And of course, you resort to this only when you cannot correct it in some other way, because this requires reading of your neighbors if your ECC is not enough to correct the current page that you're reading. And as far as I know, some sort of this is actually implemented in some flash controllers. Okay, we've studied also data retention. Data retention is actually really, really interesting. And just like we disturb prone and redisturb resistant cells, there are data retention prone and data retention resistant cells also, and you can take advantage of this. So there's a lot more over here. This is a more theoretical paper that actually does a lot of online flash channel modeling that I'm not going to talk about at this point. But I think the real interesting thing right now in flash memory is, as I said, flash memory was not scaling very well because the size was reducing and you were getting a lot of error effects. But manufacturers figured out how to 3D stack flash cells. As a result, now they have layers of flash cells. And that enabled them to increase the size of the flash cell. They were at 1x nanometers, let's say 15 nanometers or so, with planar flash. When they moved to 3D flash, they increased the cell size to 40, 45 nanometers. Now these cells are much bigger, and the way they gain capacity is by going vertical. But of course, this has now different types of error mechanisms that we cover in these papers, like layer-to-layer process variation. Some layers are much worse than others. And also, if you cannot keep adding layers, at some point you'll still need to keep reducing the size of the cell. And I think that's going to be inevitable, no question about that. And as a result, you will actually get to the same kind of errors, and maybe different kind. You also have errors that are influenced by the vertical stacking of the cells. Actually, here we, for example, characterize that process variation that you have because of the vertical stacking. And there's this phenomenon called that early retention loss. After you program a cell, you lose retention very, very quickly at the very beginning. How do you handle that becomes interesting. But I'm not going to talk about that. And I think we've done well. Any questions? Yes?
What about no flash?
No flash.
Yeah.
What does that mean?
No flash. No, there is another. Supposed to NAND flash. Contrast to NAND.
Oh, I see. Okay, NOR flash. Yeah, NOR flash is not as scalable as NAND flash. That's the problem, yes.
Yeah, but there you don't access in pages, you know.
That's right, but it's more expensive. It's lower latency, sure. Yeah, but I think it's not as scalable. That's the downside. Yeah. That's true. So I think, unless some technology breakthrough comes through, NOR flash may not have as wide applications as NAND flash. NAND flash was very successful because it was very scalable, right? You got very high capacities very quickly. Exactly, yeah. That's why we were not as interested in NOR flash. It's interesting probably from a small market domain, for a small market domain. And also scientifically it's interesting, sure. But
the problem that we have specified is for NAND flash.
Yeah, these problems are for NAND flash, yes. Yeah, we always say NAND over here. It's not for NAND NOR flash, you're right. Any other questions? Okay, so let's take the lunch break now. We'll be back soon.